Welcome to a mind-bending exploration of our planet's history. Most of us are confident we're the first technological civilization to roam the Earth. But what if we're wrong? No, we're probably not. But how certain can we really be? A popular method to gauge the likelihood of extraterrestrial life is the infamous Drake equation. This equation estimates the number of intelligent civilizations in our galaxy by multiplying various factors, including the number of habitable planets, the chance of life forming, the emergence of technological life, and how long such civilizations persist. Scientists have identified billions of potentially habitable planets in our galaxy. However, the other parameters remain challenging to estimate. Why? Because we only have one reference point for life and civilization, and so far we've got 0 confirmed cases of a technological species going extinct. Although at the rate we're going, we might soon add ourselves to that list. If we were to find just one more instance of life or technology, we could significantly revise our estimates of how common it is for any given planet to develop intelligent beings. There's some tantalizing, though weak evidence that life may have started independently on Earth, not just once, but perhaps twice. A zircon crystal found in Western Australia contains a speck of carbon that appears to have been processed through a living organism. It shows a higher ratio of carbon-12 to carbon-13, a telltale sign of biological activity. If life did start up again after such a major extinction event, that means a biogenesis, or life emerging from non-life, could happen much quicker than we thought. This would require us to adjust our Drake equation to reflect a higher likelihood of life developing on suitable planets. However, this is all speculative. One of the main reasons it's difficult to verify life's origins is the scarcity of early fossils. Only Greenland and a tiny piece of Western Australia remain from that primordial era. As most of the Earth's crust has been recycled through tectonic processes, future inhabitants of Earth may have barely any evidence that we ever existed. So, could we be certain that we are the first technological civilization? If we're not, that would have significant implications for our Drake equation, pushing us to rethink the probabilities of civilizations emerging from life and how long they last. Let's be clear, neither Schmidt nor Frank believes such a civilization existed. The burden of proof is significant, and there's currently no real evidence supporting the idea. The question becomes, could a non-human industrial civilization have existed before us? If so, how long ago might it have existed, and what remnants could we look for today? To start contemplating what evidence a prior civilization might have left behind, let's consider what our civilization will appear like in the far future. Homo sapiens have existed for about 300,000 years, but our significant impact has been felt for around 10,000 years during the Anthropocene era, marked by our profound influence on the planet. This impact has ramped up tremendously in the last 300 years since the Industrial Revolution. You might assume that our constructions, skyscrapers, bridges, and monuments will be the most telling signs of our existence. However, that won't be the case for long. While the pyramids of Giza might stand for millennia, they won't last for millions of years. Our bustling cities will eventually erode, get buried or washed away, or be transformed into deserts and ocean floors. Many remnants will be drawn beneath shifting tectonic plates, eventually being reformed into new rock, essentially erasing any memory of their existence. But will future civilizations spot signs of our once thriving culture? Geological recycling means anything older than 500 million years is practically gone. While we've accessed samples from various geological eras, we've only examined a tiny fraction of the Earth's surface from before the Quaternary period, which began around 2.6 million years ago. Modern urban land coverage accounts for less than 1% of the Earth's surface today. So, if a civilization like ours existed millions of years ago, it's extremely unlikely we'd find physical remnants, including cities or artifacts. Let's not forget that fossilization is rare. Take the dinosaurs. They existed for about 240 million years before going extinct around 65 million years ago. In that vast stretch of time, we have only a handful of specimens. When you compare our mere 10,000 years of civilization, it barely registers in the fossil record, with our industrial era almost non-existent in it. To track geological time, scientists often rely on sedimentary rock. This rock forms from the accumulation of dead marine organisms on the ocean floor over millions of years. By analyzing these layers, exposed or extracted through deep drilling, we gain insights into changes in ocean chemistry, temperature, and biological content, reflecting broader planetary conditions. The Anthropocene might be represented by only a few centimeters thick layer amidst kilometers of sedimentary deposits. Within this layer, the Industrial Age represents an even tinier fraction, perhaps mere millimeters at most. Although future civilizations might not find our bones or artifacts, they could recognize this wafer-thin layer in the geological record. The term Anthropocene denotes this era dominated by human influence, which could become a significant geological marker once officially recognized. Geological eras are defined by distinct changes in the geological record, and the Anthropocene fits the bill. The markers created by our activities today resemble past transitions that took place millions of years ago. To assess whether earlier events might be linked to industrial activity, we explore the signals embedded in Earth's geological layers. We begin with chemical and isotopic imbalances caused by our activities. Industrial pollutants like heavy metals and long-lasting chemicals, including CFCs, alter the planet's chemistry. Waste, ranging from rare earth elements to plastics, contributes to these imbalances. Nitrogen fertilizers and pharmaceuticals leave their mark too. Radioactive isotopes from nuclear weapons testing will persist in the geological record for tens of millions of years. The loss of biodiversity won't necessarily show up as distinct layers, but will be reflected in a decline in biodiversity indicators. Our most significant geological impact is climate change. Over the Industrial Revolution, we've released approximately 500 billion tons of carbon, primarily rich in the C12 isotope, into the atmosphere. This influx skews carbon isotope ratios in the air, soil, and oceans, which will eventually be reflected in the sedimentary layers we're creating today. The rise in temperatures associated with this atmospheric carbon will leave traces in the geological record in multiple ways. Increased rainfall and rising sea levels will accelerate erosion, while warmer oceans will release more dissolved CO2, boosting their acidity and altering the fauna that can survive there. All these factors will contribute to shaping the planet's future. If you enjoyed this content, don't forget to like this video. Share your thoughts in the comments below and subscribe for more interesting insights on our impact on Earth.